we are back again. So next we will go for coupled circuit, right. So this I told you that in fundamentals of electrical engineering, coupled circuits, its convention, other things, how to take mutual induced voltage plus or minus sign, everything is explained in detail, right. So just to brush up our memories for this course, right. So just I have taken a different example, right. So you have here you have a before giving the nomenclature, here you have two coils, and your what we call this a coupled circuit. This the turn of this number of turns of this coil is N1. This is your N1, and number of turns of this coil is N2, right. And the resistance of this coil is R1, and it is here R2, right. And this voltage is E1, this voltage is E2, and now both the currents I1 I2 entering into the your what you call into this coil, right. And direction of the flux, other thing can be applied to your right hand rule, right. And now question is that these things, this whenever you have your current is flowing through this, then the flux, what will happen, part of the flux will link this coil N1, right, and part of this will link this coil that is mutual one, that is your this coil, that is second coil, right, whose number of turns is N2, right. So that means your what you call, that is your phi M1 because of this one. Similarly, when if you have current I2, then it will your what you call self linkage is your flux will be phi L2, right, and because of this current some flux also phi M2 will link this coil, right. So in this case your phi M is equal to phi M plus phi M2. So both, if you what you call that, if you take the your what you call that your right hand rule, then you will find these two will be additive. For this I refer to the fundamentals of electrical engineering, right, that magnetic circuit. So and these two are your N1 N2 number of turns, and from that we will write that equation, right. So in that case, actually for right hand rule is that this is your coil. If you grasp the coil like this in the direction of the current, then this will be the direction of the flux, the thumb will be direction of the flux. So in this case this is phi 1, and this is entering also if you direction of the current, if you grasp it, right, so it will be also in the downward direction, and this will be upward directions. So that's why these two are plus phi M1 plus phi M2. So that's why I refer it, I request you that just have a look on that if you have any doubt. Otherwise I believe that you know this, right. So this is your what you call the coupled coil. Now how to coupled circuit, how to write those equations. So in this case your this is magnetically coupled circuit. Now phi L1, the leakage flux linking winding 1 only, this is only they are linking only winding 1. Phi L2, leakage flux linking winding 2 only, so this is your winding 2, right. And phi M1, mutual flux linking both windings due to current in winding 1 acting alone. I mean this is your phi M1. So because of this your what you call, because of this current in I1, most of the flux will link this your coil 1, and part of this also your what you call link that your what you call that other coil. Apart from this coil, other coil, that means total flux linkage of this coil, that is N1 number of turns. Basically you have phi L1 plus phi M1, because phi L1 self linkage, right, plus this phi M1, but this phi M1 also will link this one. Similarly for your other one, right, phi L2 will be there, and phi M2 also will link this one. So total flux linkage of this coil will be phi L2 plus phi M2, but this phi M2 also will link this one, and this phi M2 because of this your current I2 in the second circuit, that is your number your what you call the other coil, right. So that's why phi M1 mutual flux linking both windings due to current in winding 1 acting alone, right. Similarly phi M2 mutual flux linking both windings due to current in winding 2 acting alone, right. So this is your what you call that your what you call the coupled circuit. Now we have to write down the few equations. Now consider the circuit shown in figure 11 consists of two magnetically coupled windings. So this is my figure 1, this is my figure 1, right, sorry, figure 11, right. And therefore the magnetic path is assumed to have linear flux MMF relationship. We will assume the linear relationship between flux and MMF, right? That is between phi and Ni, right? The winding currents I1 and I2 are considered positive into the winding as shown in figure 11. So as these two currents are entering into this coil, we are assuming it is positive, right? Some convention we have to make. Therefore, the terminal voltages you can write for E1 will be d psi 1 upon dt plus I1 R1. And for this coil, if you write the terminal voltage E1, it will be I1 R1 into your d psi by your dt, right? So that is your d psi 1 by dt for coil 1. Similarly, for coil 2, E2 will be d psi 2 by dt plus I2 R2. So psi 1, psi 2 are the flux linkages, right? The magnetic field is determined by currents in both windings, right? Because both winding currents are there, therefore psi 1 and psi 2 are the flux linkages with the respective windings produced by the total effect of both currents, right? Thus, we can write psi 1 is equal to N1 into phi M1 plus phi L1 plus N1 into your what you call phi M2. Now, if you come to that, if you come to this circuit, right? I mean, why I am telling this? When I write the synchronization equation, directly will write, and you will find it easy. For this coil, see your what you call the flux linkages, right? One is that your what you call that psi 1 for this thing, that psi 1 is equal to that one thing is there, that is phi L1 is there plus phi M1, this phi M1 is also there, right? So phi M1 is also there. So that means psi 1 is equal to current is I1, right? So from that you can make out that your what will be the flux linkage, right? Over turns. So in that case it will be N1 into psi L1 plus your psi M1 plus, because of this thing psi M2 also, there is a flux linkage of psi M2 here, so it will be N1 into psi M2, phi M2, right? So that means that's why this equation is written that N1 into phi M1 plus phi L1. This is your what you call that your phi L1 plus phi M1 already linking N1, and this phi M2 is coming because of the current in the second coil I2 linking this flux the coil your 1, that is number of turns N1. So that was N1 into phi M2. Similarly, this is equation 12. Similarly, psi 2 will be N2 into phi M2 plus phi L2 plus N2 into psi M1, just other way, right? And this is your psi 1 and psi 2, the flux linkages, right? So that means the flux linkages can be expressed in terms of self and mutual inductances, whose expressions are given below, right? We will see that self inductance by definition is the flux linkage per unit current in the same winding, that you know this, right? So accordingly, the self inductances of windings 1 and 2 are respectively, you can write L11 will be N1 into psi M1 phi M1 plus phi L1 upon I1, because if you come to this diagram, this because of this current I1, the flux linkage actually phi L1 plus phi M1, right? So and similarly, because of this current I2, flux link is this coil, right? Phi M2 plus phi L2, and other thing that is mutual one linking, that is your what you call that phi M1 linking this coil also. Similarly, phi M2 flux linking this coil also. But our interest is now self inductance, so it will be basically phi L1 plus your flux linking this coil phi L1 plus phi M1. So that's why we are writing that self inductance is this one, your L11 N1 into phi M1 plus phi L1 divided by I1, right? Similarly, for L22, just same thing, N2 into phi M2 plus phi L2 upon I2. This is 14 and 15, these two equation number, right? Or we can write L1 is equal to L11 is equal to LM1 plus your LL1. That means that things what we are writing actually, this term, say this term you can break it like this. It is N1 your phi M1 divided by I1 plus you can write N1 phi L1 divided by I1, right? So this term N1 phi M1 by I1, this is your this one, and this term N1 phi L1, this is your this term, right? So this is equation 16. So similarly, your L22, similarly it will be Lm2, it is nothing but N2 phi M2 upon I2, this is Lm2, plus your N2 phi L2 upon I2, this is Ll2, this is equation 17, right, where Lm1 and Lm2 are the magnetizing inductances, right, or sometimes we call mutual inductances, right, and Ll1 and Ll2 are the leakage inductances of the respective windings. So just hold on. So now mutual inductance between two windings by definition is the flux linkage with one winding per unit current in the other winding. Therefore, the mutual inductances between windings 1 and 2 are, this also you know, right. So this is your mutual inductance between two windings by definition is the flux linkage with one winding per unit current in the other winding. Therefore, the mutual inductances between windings 1 and 2 are L12 will be N1 into phi M2, and it is actually this phi M2, this flux, actually mutual flux, that is linking the coil 1 whose turn is N1, and that is due to the current is I2. So you can write L12 is equal to N1 phi M2 upon I2. This is your equation 18, right. Similarly L21 will be N2 into phi M1 upon I1. This is equation 19, right. So if you assume that P is the permeance of the mutual flux path, then we know that phi M1 will be N1 I1 into P, right. So we know MMF into permeance is equal to flux linkage. So but in terms of your what you call P, the permeance of the mutual flux path, then we can write phi M1 is equal to N1 I1 into P. Similarly, pi M2 is equal to N2 I2 into P, right. Now equation 18, 19, 20 and 21, if you use 18, 19, 20 and 21, you will get L12 is equal to L21 is equal to N1 N2 is equal to P, right. That means this equation, your what you call your, just hold on, I will make it for you. This equation you multiply numerator and denominator by your N1 N2, right, is by N1. So if you do so, just hold on, I will go to the equation 18, that will be easier, right. Just hold on. This equation, if you multiply by your N1, your N1 is there, multiply numerator and denominator by your N2, right, and if you do so, then just hold on, space is not there, I am making it here, this equation I am making it here. It is N1, then numerator and denominator you multiply by N2, this is N2, then this one you can write phi M2 by your N2 into I2, right. So this is nothing but your permeance, this is your flux by your what you call that your MMF, this is N2 in I2, right. So this one you can make it as a P, right, that is the permeance. So that similarly this one, if you multiply this one by your N1 term, then it will be N1 N2, right, it will be N1 N2, then this one you can write phi M1 upon N1 I1. This is also expression for permeance, right. So that's why if you do so, that means, so that's why this equation can be written as your phi M1 is equal to N1 I1 P, phi M2 we have already written. Therefore these two will find L12 is equal to L21 because N1 N2 into P, because these permeance expressions are given here. P but your permeance for the path P will remain same, right, what your right. Therefore P is equal to your phi M1 upon N1 I1 or is equal to phi M2 upon N2 I2. So basically it will be N1 N2 into P, right. So this is L12 is equal to L21 is equal to N1 N2 P. So they are same. This is equation 22, right. So substitution of equation 16 to 19 in equation 12 and 13, you would give the following expression for flux linkage of winding 1 and 2 in terms of self and mutual inductance. So if you substitution of equation 16 to 19, that means your whatever you have in the previous page 16 to 19, right, 16, 17, 18 and 19, right. So in equation 12 and 13, just you do this, I am not going back, right, it's a very simple thing, just to do this. So you will get the flux linkage psi 1 will be L11 I1 plus L12 I2, right? That is equation 23. And similarly, psi 2 will be L21 I1 plus L22 I2. This is equation 24. So in the above equations, it is important to recognize the relative direction of self and mutual flux linkages by the use of the appropriate algebraic sign for the mutual inductance, right? So the mutual inductance is positive if positive currents in the two windings produce self and mutual fluxes in the same direction, right? So that you have to, this is from your, this you have to keep it in your mind. The mutual inductance, that is your, I am just underlining again, the mutual inductance is positive if positive currents in the two windings produce self and mutual fluxes in the same direction, that is the fluxes add up, right? So there we have seen no phi 1 plus phi 2, right? And just you apply your right hand rule and change the direction of the current and have a look. That's why I refer again and again the magnetic and coupled circuit. You read any book or that fundamentals of electrical engineering course, the magnetic circuit portion, just brush up your memories if you have, if you want to have a look on it, right? That is the fluxes add up, otherwise it is negative, right? Therefore equation 10 and 11 for voltage together with equation 23 and 24 for flux linkage give the performance equation of the linear static coupled circuit, right? That is of figure 11. So now an inductance actually represents the proportionality between a flux linkage and a current, right? As seen from equation 9 and 22, an inductance is directly proportional to the performance of the associated flux path, right? That we have seen. Now once this is done, right, then we have to see the basic equations of a synchronous machine, right? So we will use the generator convention for polarities so that the positive direction of the stator winding current is assumed to be out of the machine. This, when you write the flux linkage equation, these things should be in your mind, that when you use the generator convention for polarities so that the positive direction of a stator winding current is assumed to be out of the machine, right? Therefore the positive direction of the field and armature currents is assumed to be into the machine. That is your figure 9, the diagram, right? I am not going to the diagram, but when we listen to the video, just open the diagram, right? So in addition to the large number of circuits involved, the fact that the mutual and self inductances of the stator circuits vary with rotor position, it complicates the synchronous machine equations. Later we will see that, right? So the variations in inductances are caused by the variation in the permeance of the magnetic flux path due to non-uniform air gap, right? So their permeations also will be very, or what you call, it will be a, it is not a constant variable, and later we will see that will be a double frequency term, right? So this is pronounced in a salient pole machine in which the permeances in the two axes are significantly different, right? Particularly for salient pole machines. Even in a round rotor machines, there are differences in the two axes due to mostly to the large number of slots associated with the field winding. Here also permeance may be different, right? Therefore the flux produced by a stator winding follows the path through the stator iron, across the air gap, through the rotor iron, and your back across the air gap. So the actually the flux produced, right, by stator winding follows through the stator iron, across the air gap, and through the rotor iron and back across the air gap. This you have studied for in synchronous machine, right? Therefore the variations in permeance of this path as a function of the rotor position can be approximated as. So what we will do is, we will approximate this permeance thing, that P is equal to P0 plus P2 cos 2 alpha. What is alpha? We will through diagram also we will see. So this is equation 25, right? In the above equation, this equation, alpha is the angular distance from the d axis along the periphery as shown in figure 12. Before this thing, this is figure 12, right? and this is your d axis. This is from this one, this alpha is measured, right, and this is your alpha, and this is minus 90, 0, 90 degree, 180 degree, 270. This is n pole, this is s pole, this is d axis, and this is q axis, right, and your and this side is the your plot of permeance, right. So when alpha is equal to, if you see this, when if you put alpha is equal to minus 90, anyway cos minus theta is equal to cos theta. So whatever it will come, that is your this is your p plot. You just put alpha is equal to minus 90 degree, put alpha is equal to 0 degree, right. If you put alpha is equal to 0 degree, it will be p0 plus p2, right. So that peak is actually p0 plus p2, right. And if you put alpha is equal to your what you call minus 90 degree, it will be cos 180 degree, right. So it will be p0 your minus p2. So this is the minimum, this is the maximum, and it is a double frequency curve, sine, your what you call sine curve, right. So variation of permeance with rotor position. So this is your alpha. So that's why this we have taken p is equal to p0 plus this is we have approximated as, right. Derivation other things we are not going for this course. We have assumed that this is valid. I mean it is valid actually, right. And so if you come to this, your what you call this thing, a double frequency variation, just now I showed, is produced since the permeance of the north pole south poles are equal, right. So that is your higher order even harmonics of permeance exist, but are small enough to be neglected. So higher order harmonics are not considered, right. Even higher order even harmonics, right, not considered. So this is your figure 12, right. This is slightly this figure is, I hope it is readable, right. Just after 3-4 hours lecture you will find everything is okay. 1 or 2 figures are like that because of scan copy from the photocopy, right. And following notations will be used in writing the equation for the stator and rotor circuit. So notation means these are the your nomenclature. So again and again I will not come, but I will tell from this thing that EA, EB, EC is equal to instantaneous stator phase to neutral voltages, right. IA, IB, IC is equal to instantaneous stator currents in phases A, B, C. EFD is equal to feed voltage, that is DC. IFD, IKD, IKQ field and armature circuit currents, right. Then RFD, capital RFD, capital RKD, capital RKQ rotor circuit resistances. This is field resistance. This is your armature winding on D axis and armature winding on Q axis. The resistances are. Then small l AA, small l BB, small l CC, this suffix, it is self inductances of stator windings, right. Then small l AB, small l BC, small l CA is equal to mutual inductances between stator windings, right. Then LAFD, small l FD, small l AKD, small l AKQ is equal to mutual inductances between stator and rotor windings, right. Then LFFD, LKKD, LKKQ, that is your self inductances of rotor circuit, right. And capital RA is equal to armature resistance per phase, and P is differential operator, that is dy dt, right, because instead of dy dt we will use your P, and later you will see many interesting your things on synchronous machine. So these are all the nomenclature, these are all the nomenclature before moving further, right. So now stator circuit equations. Now the voltage equations of the 3 phases are, if you go back to the, whenever you read this thing, I am not going back, you please go to figure 9, right, you and just see this, how we are writing this, you just see this. If you look at the circuit of figure 9, everything is coming from figure 9, right. So I am not going back, right. So then little bit time will be saved. Just when you will see, my suggestion to you, when you read this thing, that figure 9 you redraw, right, draw the whole circuit, or if you have a download and you can have a printout also, no problem, right. And just see this one, that how you can write looking at the flux linkage equation and the direction, right. So it basically it will be EA plus IARA is equal to d phi A upon dt. Look at the direction of the flux linkage, whatever is given, and the EAEBEC, right. So the polarity. So EA is equal to, then you can write d phi a, d psi a upon dt minus IARA, and d by dt is equal to P, right. That is your, I to mention you, the differential operator will take d by dt. Therefore, this equation you can write P psi a minus IARA. This is equation 26. Similarly, EB is equal to, you can write P psi b minus IB RB, it is 27. P is nothing but a differential operator d by dt, right. And EC is equal to P psi c minus IC RC for phase C. This is equation 28. Therefore, the flux linkage in the phase A winding at any instant is given by like this. I told you that look at the direction of the flux, and I told you also look at the figure 9, and the convention we have taken when current leaving the terminal A, B, C, we have taken positive direction, and for the field winding and for the damper windings on the D axis or amorcer winding on the D axis or Q axis, when it entering it we have taken the positive direction, and when the current actually leaving the terminal of the stator side, that is IA, IB, IC, you have taken positive convention. And look at the flux linkage in your figure 9, right. Just imagine that figure 9. So psi a will be, it will be, you can write, it will be minus LA IA, right. Then minus the mutual one will come LAB IB and minus LAC IC, right. Look at the direction of flux linkage and direction of the current, the way we have taken your what you call the current leaving the terminal is a positive convention for generator, right. Only this part little bit very easy actually to write those equations, right. Nothing to be your what you call confused, straightforward you can write. And other is, and when you write that all the mutual thing, right, that is plus direction, because current entering into this field winding as well as current your what you call in the positive direction you have taken. Similarly for the amorcer winding on the D axis and Q axis. So you can write plus LAFD, all the nomenclature is given, IFD plus LAKD IKD plus LAKQ IKQ. This is equation 29. Similarly for phase B and phase C can be written, but we will see later, right. So similar expressions apply to flux linkage of windings B and C. We will see later because we have to consider all, right. The units used are Webers, Henrys and amperes, right. So the negative sign associated with the stator winding currents is due to their assumed direction. I just told you, right. All the inductances is equation 29 are functions of the rotor position and are thus time varying. So all this inductance it depends on the rotor, actually function of the rotor position, and they are time varying. That means this makes things more mathematically more complicated, right. So stator now all these things are what you call the stator self inductances. The self inductance LAA is equal to the ratio of the flux linking phase A winding to the currents LIA with currents in all other circuit equal to 0. Same just when we are reviewing the magnetic circuit, philosophies remain same, right. Philosophies remain same. The inductance is directly proportional to the permeance. That also we have seen, which is indicated earlier has a second harmonic variation, right. The inductance LA will be maximum for theta is equal to 0 and a minimum for theta is equal to 90 degree, a maximum again for theta is equal to 180 degree and so on, right. Therefore, if you neglect the space harmonics, right, the MMF of phase A has a sinusoidal distribution in space with its peak centered on the phase A axis. Therefore, the peak amplitude of the MMF wave is equal to NA IA, that is that you are what you call ampere turns, right, where NA is the effective turns per phase. So as shown in figure 13, right. So this is your, as shown in figure 13, this can be resolved into two other sinusoidally distributed MMFs, one centered on the D axis and other on the Q axis. Now this thing is that we know that you are what you call that this is my MMF, say NAIA, right, and on that one component is NA, this is D axis Q axis, one component NAIA cos theta, another is minus NAIA sin theta. Now if you look into this, this is my your what you call MMF for phase A. Suppose this is the MMF plot, right, this is the MMF plot, and you know that from axis phase D axis actually leading the phase A by an angle theta. That's why this theta is marked, and Q axis leading this one, that is total is 90 degree plus theta, right, and this is my MMF A. Now if you just make it the two component, this is MMF your for phase A along D axis, and this is another one, that MMF, that for phase A, your what you call MMF, that is your two breakup we are taking. This is MMF A. One is along D axis, that is MMF AD, and this is along Q axis, MMF AQ, right? So if you look into this, that one is NAIA cos theta, because D axis is leading phase A by an angle theta, and Q axis leading phase A by angle 90 degree plus theta. Earlier we have seen, again we will go back to figure 9, right? Again we will go back to figure 9, everything is marked there. So in this case, when you write your NAIA, it is becoming basically, what will become? It will become NA, it will become NAIA, then it is sine your what you call, that one is cos theta, another is your what you call minus NAIA sine theta, right? So whenever, because that is your cos 90 degree, your what you call, that your cos 90 degree plus theta, so this side will become your minus NAIA, this one will become minus NAIA sine theta. So NAIA cos theta, and another will be minus your NAIA cos 90 degree plus theta, right? That will be your minus NAIA your sine theta, right? So these two components, that's why it is minus NAIA sine theta. This is phase MM wave, for its your what you call, this is phase A MM wave and its components. So two components, your two components for this thing, your one is your along D axis, another is along Q axis. Actually this makes our analysis, you will be little bit simpler. Later we will see that, right? With this, thank you very much. We will back again.